points explicitly and building solutions for half of the data that we're generating. You generate a metric, train on it, and then feed it forward to extrapolate dependence on complex structure. So it was sort of a direct minimization problem for certain complex structures, and then you can extrapolate for others.
I see. So I see. Okay. I see. Okay. Thanks a lot. Thank you. Yeah.
Thank you. Thank you, Lara. Thank you, everyone.
Thank you very much.
Yeah. Okay. So our next speaker is Nemani. Nemani, are you there?
Yeah. Can you hear me?
Yes. Can you please share your screen?
Yes.
Excellent. Okay. Nemani, I'll tell you for 25 minutes. Okay.
Yeah. Again, can I just request you something? In case there is an interruption in my signal, I'll take just 1 minute to switch over to something.
No problem.
Okay.
No problem. Please go.
Okay. Thanks. So let me start by thanking the organizers for this nice meeting, and happy to be at IIT Roorkee virtually, though I would have preferred to be there physically. So this talk is going to be based on this work that I did with Nishant, is my student, and 𝗬𝗫𝗶𝗿, who's a postdoc at CMI, who also gave a talk earlier in the day. So the aim of the talk is going to be to show that four-dimensional flat space gravity admits some novel boundary conditions with asymptotic symmetry algebra that includes a chiral SL2 current algebra plus a few more currents. So let me start. So I'll give a brief introduction because you have heard several talks on this topic. So in the past few years, it is fair to say that there has been considerable progress in the project of flat space holography. Flat space holography seeks a holographic description or a hologram of a gravitational theory. In particular, for four-dimensional flat space gravity, what one means by is that any theory that includes the Lorentzian two-derivative gravity without cosmological constant, of course, and with asymptotically flat boundary conditions. And Lorentzian geometries that I'll be interested in could either have 1,3 signature or 2,2 signature. And the boundary of, say, 1,3 signature Minkowski space has several components, but the massless particles reach the null infinity. Okay, so at future null infinity, the metric is usually taken in these coordinates. These are called boundary coordinates, minus du square minus 2 du dr plus r square d omega 2 square, where this is just the metric of a round to sphere written in Fubini-Study form. One also works sometimes with this metric, which is not quite this, so that it's not a sphere, but a plane at infinity. These are also coordinates for flat space. The corresponding metrics in the patch near sky minus are obtained by time reversal, which acts on u going to minus v, interchange of u with minus v. The continuous isometries of these Poincare Minkowski spaces are, of course, Poincare algebra, ISO 1,3. I will write the generators of these 10 generators of the Poincare group as ln, ln bar, and PRS, where ln's form an SL2C, ln bars form their conjugate SL2Cs, and these PRS are in the bifundamentals of these two SL2s. If I'm working with 2,2 signature, of course, this will be SL2R plus SL2R bar. They will be independent as opposed to be complex conjugate to each other. The boundary at near sky plus includes, or you can actually say that the boundary is just the two-dimensional sphere instead of being a three-dimensional object, because the u direction, the du square, is subleading. This part is r square, whereas this part is r1. So the boundary is actually two-dimensional. It's like, suppose radius 3 times s1 or something. The boundary is actually two-dimensional, even though you may have thought it's four-dimensional geometry, but it's like three-dimensional boundary, but that's not so. So the hologram of flat space gravity should probably live on this celestial sphere, and there has been a very strong candidate for what that hologram should be, which is named celestial CFT. And there's a lot of work in understanding what this object actually is. And there was a very nice talk earlier in the conference about this. So I will have very little to say about that. So what should be the symmetries of the holographic dual of flat space? They should match with the asymptotic symmetries of bulk gravity theory. If you impose Dirichlet boundary conditions for metric at sky plus, say, for example, holding the metric on S2 to be held fixed to be the round S2 metric, then the answer is well known, and that's called BMS4 algebra. And BMS4 algebra is the same as what I wrote. It takes the same form, except that this PRS, the indices on R and S, are not just ±1, but any Z plus half, any odd integral multiples of half. There appeared in the literature further extensions of BMS4, which are motivated mainly by trying to derive the soft theorems from word identities. So one such extension is called extended BMS4, where these two copies of SL2 are lifted to Verassoros. Another extension of BMS4 is called the generalized BMS4. There are experts in Chennai who have introduced this, where this, again, the Lorentz part of the Poincaré group is extended to volume preserving smooth diffeomorphisms on H2. On a different track, why can't I see this myself? Okay. On a different track, by looking at the, sorry, just give me a second. Yeah, by examining the OPs of gravitational operators, graviton operators in the celestial CFT, Banerjee and 𝗰𝗶𝗶𝗍 and others were able to uncover an SL2 current algebra, mainly looking at the MHV amplitudes at tree level from the point of view of celestial CFT. Their algebra contained 6 holomorphic currents, which I label them as J, A, T, and PR, where these A's run over 0, plus minus 1, and R again are plus and minus half. The weights of these guys, or the representations they belong to, are labeled by these. So these labels are such that H minus H bar is always 2, which correspond to these being closely related to positive helicity graviton operators in their soft limits. And these negative representations simply mean that on the right side, they are finite dimensional. So that just tells you that this is a vector, and this is a J equals half representation, whereas this is a singlet. And this is like a stress tensor. This is like a, from the left, holomorphic diffeomorphisms are concerned. This is like a quasi stress tensor, and this is like a current, and these are spin 3 half objects. The mode algebra of these currents is not BMS4. It doesn't contain BMS4, but it does contain ISO 1,3, the Poincaré algebra, but it's a chiral extension of it. So the limited question I want to answer today is, can this chiral algebra be embedded into a gravitational theory by appropriate definition of boundary conditions? The answer is yes, and that's what I'm going to tell you. So in what follows, I will spell out boundary conditions for flat space gravity that will be consistent with variational problem and with the asymptotic symmetry algebra, same as the chiral algebra, that I have not written down here because it will appear anyway. I will derive it. So, or you may have seen it in Partho's talk earlier in the day. I will mostly use the language of 1,3 signature. However, whatever I say is easily applicable to 2,2 signature. All that you have to do is to take the Z bar and interpret them as 2 light cone coordinates again. So we'll use the expansion of the metric around scribe plus. So I will work in that patch. Again, use the same coordinates that I introduced earlier, I use Z bar, and use this so-called Neumann-Unti gauge, which is basically says that, yes? No? Okay. So any component of the metric which has at least one leg along R is fixed. Most of them are 0, and this particular one is -1. So that means it's effectively becomes 3×3. Expansion becomes 3×3 matrix, which are Gij along the coordinates U, Z, Z bar. I and J take coordinates U, Z, Z bar. And I will take the expansion, which is consistent with the asymptotic flat space, where no metric component can grow faster than R square. So that's what this expansion means. N equals 0 corresponds to R square term, and everything else is suppressed in powers of 1 over R. And the equation of motion that I'm going to use is the Einstein's equation, which is Ricci flatness in 4 dimensions. And I'm also going to impose this asymptotic flatness condition, which is basically the Ricci tensor with 1 up, 3 down indices has to go to 0 as R goes to infinity. And then the equations, these equations can be solved for Gij(n) order by order in 1 over R. And the first condition that you get is that this G0 guy has to be degenerate. And because I'm interested in, again, matching with the asymptotic flatness conditions, I'm going to assume that G0 is of rank 2, and I'll take it as in a particular form. Again, I'll take it in such that any component which has a leg along U is 0. So therefore, G0 essentially has 2 by 2 component, which I take to be non-degenerate. Then another condition that tells me that this G0AB has to be, its time dependence or U dependence has to be outside. It has to be a conformal factor. Okay, and I'm going to again assume, this is an assumption, that this omega is actually U independent. This then implies that G1 components also along anything which has a U leg in it also vanish. So again, G1 also reduces to just G1AB instead of G1ij, where AB run over coordinates Z and Z bar. Okay, and one last condition one has to impose to set up a good series expansion is one condition in the Neumann-2 gauge, which translates to saying that this G1, which is left out, is traceless with respect to G0. So with these conditions, you can just keep solving these equations, and you will find some undetermined equations from once in a while. You put that as physical data and just keep going. There's one additional condition that we get more than what people usually get by imposing the stronger version of Riemann vanishing, is that G1AB has to be at most linear nu. Okay, so that means G1 is splits into 2 functions, G10 and G11. And then there are additional differential conditions. So for example, this is 2 of those. Okay, and the rest of the components, for example, G2, some parts of them will be determined in terms of G0 and G1, but some parts will be undetermined, and so on. You can just carry on this exercise, and many people have done this. However, to study the asymptotic symmetries of these Ricci flat and asymptotically flat solutions, one doesn't need the full set of solution space. Okay, what I want to claim is that it is sufficient to find the locally flat solutions that share the asymptotes that have been derived so far. Okay, so there are a bunch of assumptions that I've put in. So what I want is all locally flat solutions which share those conditions. Then in flat space gravity, one has to define what the configuration space is. Then what I will do is to define the configuration space to be all those G mu nus, the 4-dimensional matrix, which approach any of these locally flat solutions. Okay, so then it's reasonable to say that the asymptotic symmetries of those configuration spaces will match with the symmetries of the spaces of locally flat solutions. By symmetries of the locally flat solution space, what I mean is that diffeomorphisms which will keep me within that class. Okay, so then what is the space of locally flat solutions? In the Neumann-2 gauge that I have been working with, the locally flat geometries take a particular form. They are polynomial in powers of R. Okay, so they take this form. So for example, the highest power is R square and the lowest power is order 1. So these functions, G2UU, G0, all these functions can be functions of U, Z, Z bar, but they're not functions of R. Okay, so then G2 will be, G2UU is given in terms of R0, blah, blah. So that means the data at G2 is completely determined in terms of the data at G1 and G0. Okay, the order 1 pieces in powers of R are given in terms of order 0 and order R square and order R pieces. But the coefficients at order R square and order R have to satisfy these differential equations. So once you find solutions of these differential equations for G0AB and G1AB, that's all you need to figure out any locally flat solution. Okay. So it turns out that these equations can be exactly solved completely. In fact, you can just make a finite coordinate transformation from a flat space, because you are looking for locally flat solutions, to figure out the solutions for these. And we have done this in our paper. So one important aspect that we used is a nice parameterization, which will be useful for us later on, of G0AB, which is the boundary metric on this, the part of the celestial sphere, if you like. I will take it in this form, where omega is the conformal factor times F. So F and F bar along the diagonal, and these guys along the off diagonal. When F and F bar are 0, of course, this omega times flat space. Okay, and these functions F bar and omega are functions of Z and Z bar alone. Then I will parameterize F and F bar in this fashion in terms of 2 new functions, zeta and zeta bar, And for those of you familiar with this, they should remind you of the Beltrami variables. Okay, this can be done. This is not unique, but this can be done. Okay, so then the solutions are given, the solutions to these two equations, such as G0, the other components of G0 and G1, are given in terms of this data, omega, zeta, zeta bar, of course, that determines G0, and this particular function of zeta and zeta bar and its derivatives, and a new function which we call epsilon. Okay, these are all functions of z and z bar, and their derivatives, which will determine G1. So as I said, once G0 and G1 are given, G2 is given completely. And the expressions for the locally flat solution can be found in our paper. They are a bit lengthy. They are not very useful here, except for I will quote some results, which will be useful for us later. Okay. Then what are the diffeomorphisms that keep us within this class of solutions that I have found so far? So those will be the 4D vector fields that leave the solution space invariant, right? So I will not give you the details of this calculation, except to say that once you set up the vector fields properly, you will find that the vector fields are given in terms of 4 functions of z and z bar. So what I call psi u0, basically what psi u0 is that psi u cannot depend on r is one of the conditions. Okay, so it can only depend on u z z bar, and in particular its u dependence will be linear u. Okay, so this is similar to what happened for the G1 ABs, which also split into linear u and independent of u components. And psi1u is related to psi1u is basically the u dependent component of psi u is related to this, and there are 2 more components of these guys. These correspond to basically the diffeomorphisms along the boundary, which is celestial sphere or the sigma 2, and these two, these are like super translations, and these are together is a Weyl transformation. In fact, it is true. You can just figure out how the boundary metric transforms under this diffeomorphism. It transforms as diffeo by the psi a zeros and a Weyl factor. Okay, so therefore the residual diffeomorphisms of the locally flat solutions that I have found so far are boundary diffeomorphisms, the 2-dimensional diffeomorphisms and Weyl transformations, plus super translations. Okay, so the algebra of these vector fields is too big for what I seek. I just need a chiral algebra, so that means I have to impose some conditions. Those conditions will come from the variational principle. Okay, so the boundary diffeomorphisms can be used to gauge fix the 2D boundary metric, okay, down to 1 independent component, because there are 2 diffeomorphisms. And the most commonly used gauge is the for the 2-dimensional matrix is the conformal gauge, which corresponds to setting f and f bar equals 0, as I told you earlier. So f and f bar is 0, then it's omega times flat. Right? So the other choice, popular choice, which is not so well known, is the so-called Polyakov gauge, where you put either f or f bar to 0. Okay, so if you put f or f bar to 0, for example, if you put f bar to 0, then there will be a component along the boundary metric which is along dz square, which fluctuates. Okay, and omega is omega could fluctuate, or it's a fixed function. In fact, I want it to be a fixed function. To proceed further, we need a variation input from variational principle. Okay, so we take the configuration space, as I said before, to be all 4-dimensional metrics in the Neumann 2 gauge and asymptotically approach to one of the locally flat solutions we have found. Okay, so to specify the delta S, you also need the boundary terms. Okay, 12 minutes. So I need boundary terms, and the usual boundary terms are given like Gibbons-Hawking-like terms. The 2 essential requirements of a Gibbons-Hawking term is that wherever you put the boundary, so it should respect the symmetries of the boundary. And also, when you vary the total action, the Einstein-Hilbert action plus the Gibbons-Hawking action, then the terms that appear in the variation in the boundary term should only have variations of the boundary metric, but not their derivatives. Okay, so I put the boundary at large but finite r in those coordinates u, r, z, z bar, you remember. And the residual symmetries, or the residual symmetries that we have talked about, which are diff and Weyl of 2 dimensions and super translations, that leave r equals r naught, turn out to be just the rigid translations in u, okay, and any diffeomorphisms along z and z bar. Okay, it is very easy to see, so please trust me on this. Okay, so we should seek boundary terms which are consistent with these symmetries. So the we are saying that the boundary is two-dimensional. So therefore, the boundary terms should be diffeomorphism invariant with respect to those boundaries. Of course, we don't demand while invariance because that will move the boundary around, because that will act on the location of where the boundary is. Unlike the full super translations, it only picks the translation, the rigid translation. Okay. So then I will seek such boundary terms for this action, which is the standard Einstein-Hilbert action. The metric components at a constant u, I will relabel them GUU component to be omega, GUA component to be VA, sigma AB to be GAB, okay, GAB to be sigma AB. Then we found that the boundary term that is required to satisfying those two conditions that I spelled out has to take this form. So it's a fairly simple looking term. Okay. And then you can compute the variation of the total action between these two, and as required, the terms will be proportional to the variations of delta, omega, delta, VA, delta, sigma AB. I will not give the explicit expressions for those. Okay. Finally, what you have to do is to make sure that this delta S vanishes for your class of solutions. That is the condition of variational principle. But you don't need them to vanish exactly, because you're expanding in powers of R. All those dangerous terms, which will be high, positive powers of R or constant, should vanish. Anything which is 1 over R, you can tolerate, because at the end of the day, you're going to take R1 to infinity. So it turns out, so you can just do this calculation. Okay. And I'm going to skip this part. So this is the variation. So you have to keep your gauge condition intact. That will reduce the terms that are involved considerably. And then one also imposes a condition like this one, because this is required, because you want to take care of this term, which is order R term. This corresponds, so our boundary conditions are such that GU2 is related to the curvature of G0. Okay. So holding this fixed is essentially saying that the Euler character of the boundary metric on sigma 2, the G0AB, should be held fixed when you take the variations. So that's not an unreasonable demand. So then we find the following results. So for example, if you take it to be Dirichlet boundary condition, so that means delta G0AB is 0, then only non-chiral choice corresponds to G11AB. You remember G11AB is basically the U-dependent part of G1AB. That should be 0. And it turns out that the asymptotic symmetry algebra in this case, the symmetry algebra of the space of flat solutions in this case, is exactly BMS4, but not extended BMS4. It's exactly BMS4. But we are interested in the Polyakov gauge. I'm going to pick a choice. So I'm going to put F bar to 0 and only let F2 fluctuate. That corresponds to delta G0 ZZ not equal to 0. So you have to use this condition in the delta L that we have talked about. So remember, note that this variation still keeps the determinant of G0AB not fluctuating, as long as omega is taken to be a fixed function. Then it can be shown that the variational principle is satisfied if you take GZ bar Z bar 1, both components along U and along 1, both these components to be 0. So what we have to do now is to impose these two conditions on the space of locally flat solutions that I found earlier. Okay, since I didn't tell you what they were exactly, so here are some components which are useful. So in particular, I want to set this to 0 and this to 0. These are the two components that are in the exact solution. So this is just the Schwarzian derivative of zeta bar with respect to Z bar. And this tau is basically related to the stress tensor of omega treated as a conformal factor, the Weil factor. And so we need to set these to 0. I'm not going to be interested in general omega. I'm going to be interested in two cases, omega equals 1 and omega equals 4 by 1 plus ZZ bar whole square. This corresponds to the second metric that I wrote down, where the boundary is C, a complex plane, whereas this corresponds to the boundary conformal factor being S2. So for these two cases, sorry?
4 minutes.
Okay, thanks. Yeah. So then, it turns out that, yes, my watch is saying 6 minutes, but okay. Okay, so then for these two, yeah, thanks. Yeah, for these two choices, it so happens that tau ZZ and tau Z bar are actually 0, in which case this part will drop out and this part has to be set to 0. that means zeta bar has to be a fractional linear transformation, z bar, like so. And the second condition leads to a determination of epsilon, which is of this form. So this guy has 4 functions of z, and this guy has 2 more functions. But this is not, if you scale g1, g2, g3, g4 by same non-zero function, then zeta bar doesn't change. So that means I can pick the determinant g1, g4 minus g2, g3 to be 1. So this gives you 5 holomorphic functions. Okay. And then you can compute gz, z1, 0, and okay. So we had used this Beltrami variation, right? Beltrami parameterization of f. And if you substitute this zeta bar here, it turns out that f is polynomial in z bar of degree 2. And these coefficients, the 3 coefficients is holomorphic functions. These will be related to the currents eventually, the SL2 currents. And gzz10 will also take a complicated looking expression. But as soon as you substitute zeta bar of this form, it again becomes linear in z bar up to the omega factor, which we have fixed to be the one or the other thing. So the result is that so far the f, the boundary component metric, is quadratic in z bar, or this particular one gzz10 is linear in z bar. And then gzz11, the u-dependent component, can also be worked out, and it takes some particular form. Okay, so let me speed up a bit. So we found the locally flat solutions, and there's one new function which is zeta itself. Okay, zeta itself. We have used zeta bar in f, but not zeta. So zeta happens to be a holomorphic function. So if you add this holomorphic function to the 5 that we counted so far, there are 6 holomorphic functions in the space of solutions. Okay, this is promising because we wanted 6 currents. Okay, so finally, what I have to do is to, once I have restricted my locally flat solutions using the variational problem and gotten a subset of locally flat solutions, what are the diffeomorphisms which keep me within this class? And the answer is that those diffeomorphisms also have 6 undetermined holomorphic functions. Okay, so, and you can pick a particular basis for those whole vector fields in this fashion, and those basis vectors will have commutation relations like these. You will recognize that this is just the SL2 current algebra without the level, because you don't see them, because these are vector field commutators, and this is just a Verasoro, okay, or Witt algebra. And this is that, it just says that under Verasoros the current algebra transforms in a particular way. And similarly, PRS, the holomorphic super translations, if you wish, also have this particular commutation relations, both under the Verasoro and current algebras. And this is exactly the algebra that Banerjee et al. Found. You have seen this before in part first talk today. Okay, finally, what one has to do is to figure out how the various fields that are in the solutions transform under these vector fields. And there are some bunch of expressions. Okay, these are what these tell us is that these functions are transform like primaries and the left diffeomorphisms, which correspond to the Verasoro generators, with some particular weights. This is like quasi-primary, quasi-stress tensor. These are like currents, and these are like spin 3 half objects. Okay, so let me make some comments before I go on further. So the locally flat solutions are parameterized by 6 holomorphic functions, and they transform non-trivially under the action of the asymptotic symmetry group. Our locally flat solutions were actually complex, even though I didn't tell you before. But if you worked in 2,2 signature, they're all real. Okay, and it seems reasonable to consider these solutions. So do the locally flat geometries by themselves form a phase space with an appropriate symplectic form? Are there non-trivial and well-defined charges that generate these transformations on locally flat solutions via Poisson brackets? Okay, so the usual charges are given as, in 4-dimensional gravity, are given by codimension 2 integrals. Whereas what this problem seems to be is like a chiral CFT, where the charges should have been contour integrals, line integrals. And another question is, are there boundary degrees of freedom? Because these are all locally flat solutions. So are there boundary degrees of freedom? And if so, what is their effective action? Sorry, 𝗰𝗶𝗶, can I just take a couple of minutes?
Yeah, okay, sure, go ahead.
Okay, thank you. So in the rest of the time I'm left, I'll just indicate to you some work that is in progress, where we argue that the effective action of the boundary degrees of freedom corresponding to all the locally flat geometries is actually a three-dimensional topological gauge theory, which says that gauge theory with the gauge group ISO 1,3 still Poincare in 4 dimensions, whose equation of motion tells you that that connection has to be flat, 3-dimensional one form gauge connection that should be flat. Okay, such similar result also appeared earlier last year. Okay, so let me just indicate how it works. So so for this, I have to go to the first order formulation where I write a gauge connection in the 4-dimensional Poincare group, where A is a one form in 4 dimensions, where ERS are the one forms which are Weil binds, and these are spin connections. Okay. Then locally flatness translates in the first order formulation to the flatness of this 4-dimensional gauge connection. Okay. However, if you look at the answers that we had used for the locally flat solutions, they were polynomial in powers of R. So you can actually solve some of these guys explicitly because they're all polynomials in R. So either R pairs or DR pairs and order 1 terms. Okay. Then you can make a gauge transformation of the 4-dimensional A to go to a 3-dimensional A, okay, by a group element G of R, which is field independent, and it's very nice. Okay, so this, for those of you who are familiar with the locally ADS3 solutions, this happens even in ADS space. You have locally flat connection in first order formulation of ADS, which goes to just flat connection on the boundary. So that means the locally flat equations in 4 dimensions are essentially equivalent to locally flat connection in 3 dimensions, but still valued in the 4-dimensional Poincare algebra. So what we were able to show, what we were able to do is to find this A for this class of solutions that I showed you after the variational problem, and asked what are the residual gauge transformations which keep me within this class, and figure out with an appropriate identification of various components of that curly A in terms of the fields that appeared in the solution space, we were able to recover exactly those transformations. But now notice that we have a 3-dimensional gauge theory. So if there are going to be charges for this 3-dimensional gauge theory, there will be codimension 2 objects. From the 4-dimensional point perspective, there will be codimension 3, exactly the appropriate for chiral CFT. So since I'm way out of time, I'm going to stop here. Okay, and this part of the work is still in progress. We were able to find charges at least as far as the diffeomorphisms, the left diffeomorphisms, which T of Z and JAs. We're still working on the charges for CR. Okay, hopefully this will appear sometime soon. Let me conclude. So I have presented some results about how to give boundary conditions for 4-dimensional flat gravity, which produces a chiral current algebra, it's a symmetry algebra. Okay, so the effective theory on the boundary degrees of freedom is actually through 3-dimensional topological theory. Unfortunately, the killing form of this is such that the simple Chern-Simons theory doesn't work. There are some comments one can make. Okay, so one interesting comment is that such current algebras were seen before. In fact, that's where my interest was, in the context of Polyakhov's induced gravity, where after the gauge fixing, they are called the chiral induced gravity theories. So does it mean that at least a subsector of the chiral celestial CFT actually includes the chiral gravity, chiral 2-dimensional gravity? One interesting thing that happens in the chiral induced gravity theory is that the stress tensor that you construct can be twisted in such a way that its central charge is 0. Again, that smells like what happens in the celestial CFT. Anyway, so there are a lot of questions that are yet to be answered. So, for example, we have heard a lot about W1 plus infinity. The algebra that I talked about is indeed is sitting inside the W1 plus infinity, but where is the W1 plus infinity is still not clear to us. Thank you. Sorry, Navamita.
No, that's fine. The last part was really very interesting. Whole talk was interesting. Last part was probably too interesting to me. Shom Datto, you have a question? Please ask.
So this boundary theory, does it supply a sort of gauge gravity correspondence for flat space?
Not yet. This just my understanding would be that this just captures the vacuum fluctuations. is all the locally flat solutions, only the vacuum fluctuations. But if you would have to put matter, for example, many people have been working out field theories which live on the Carolean manifolds, which would admit appropriate boundary conditions. Nishant and I also wrote a paper about this. So I don't think this is the full story, but this should be part of the story, at least in a subsector of the celestial CFT.
Okay, thanks.
Any other question? Okay, and since we are really going very tight on time, Nemani, but I would like to ask you something, but I would ask you later.
Okay.
Thank you for the talk. So
thank you. I'll stop sharing.
Yeah. So our next speaker is Gaiotto. So I cannot see him.
Yeah, unfortunately, he's not in. I just sent him a reminder.
Excellent. Nemani, you are still there?
I am still here, yes.
Okay. So one question is, if I understand, then you're basically relaxing the geometry a bit. You are not only just looking for asymptotically flat solutions or the properties of asymptotically flat spaces, but as well as Ricci flat spaces, right?
That's right.
Okay, and towards the end, you were trying to construct the boundary theory that will have exactly the same symmetry as the symmetry that you have constructed. Is that the idea?
That's right. So, so there are two steps, right? So I wanted to solve the equations of motion of the bulk, which are Ricci flatness, and then also I imposed the asymptotic flatness.
Yes.
So the full configuration space can be thought of as all the configurations which approach to one or the other of the locally flat solutions. So, so therefore, locally flat solutions should be part of the full configuration space, right? And of course, the full configuration space should approach to these guys. So the locally flat solution should by themselves capture the boundary degrees of freedom.
Yes.
Right. So locally, that's what I did. So what the Chen-Simons theory, the three-dimensional, whatever the topological theory for which the flat connections are the equations of motion, are the solutions to the equation of motion, should be capturing the boundary degrees of freedom.
Yes.
Corresponding to the large diffeomorphisms that I made to get the locally flat
solutions. Yes. I mean, this is very similar to ADS3 kind
That's
of
right.
thing.
But
just one question. So in this case, I mean, even if I didn't consider that extended BMS4, right? I mean, even without those charges, those J charges, this boundary construction should still have been possible, right?
This boundary construction is possible without specifying what variational principle you have imposed. That's true.
Okay. I'll talk to you later again in details because okay, great. So Alok, do we have David? Oh, there is another question from Harvinder. Harvinder, please go ahead. Did I understand it wrong?
Is it there?
Or
is written it here or what?
No.
Okay.
It's Harvinder, right?
The hand is raised, but
hand is raised. Yeah. He's unmuted also.
Okay.
So yes, Harvinder. Hi.
Oh, sorry. Yeah. So I am asking that you only considering gravity and there is no matter. There can be situation where you can have matter fields also.
Yes.
In the system, no?
Yes.
So what will be the situation in that case? Your celestial gravity situation.
I don't know. So you have to consider the fall-off behavior for matter as well. And for example, if you have Maxwell field or Yang-Mills fields, then you would have additional asymptotic symmetries, right? So at least this part will be there, and there could be some additional parts.
So you still expect to be a celestial CFT there with some different kind?
Yeah, I mean, that's the lore, right? So, I mean, the boundary is two-dimensional, strictly speaking. So if the holographic dual exists, then it should be a conformal field theory there with some set of symmetries. So people are still grappling about what the correct set of symmetries are, right? So, yeah.
And when your situation is Euclidean, suppose you Euclideanize your bulk, then on the boundary, how this goes?
Right. So this null infinity goes away, no? So if you Euclideanize, so things are much simpler, I would say. because now this just the spatial sphere or something is the boundary. The Lorentzian things are much more fun. So you would want to set up the holographic dual for the Lorentzian theory. Yeah, I don't know what else to say about it.
Yeah, I think you have answered my
Yeah.
question. Thank you.
Thanks. Any other question? I think I don't see any hands.
Yeah, so
Yeah.
I have another question. So if you just have the gravity theory in the bulk,
Yes.
if you just have, say, Einstein gravity or something, then don't you have a bulk bound, I mean, don't you have a gauge gravity correspondence?
We don't know, right? So if it's if bulk theory is a topological theory, then it may be a consistent quantum field theory by itself. Otherwise, you would have to embed it in some string theory or some other consistent quantum field theory like higher spin theory or something. So yeah.
Alok, is there any update?